Hello everybody, welcome to Cranky Calculus. We're here to talk about the second derivative test. Before we get started, do not forget to like and subscribe, and also please download those free set of notes that we have in the description along with those notes keys so that you don't miss out on anything. So what is the second derivative test? It's a test where we need to make sure that the second derivative is continuous in the neighborhood of C. That just means it needs to be continuous where we're looking for maxes and mins. And then so if we have a critical point, which just means that f prime of c is equal to 0, that particular type of critical point, and the second derivative is positive, that means that we're going to be concave up. You can see there we're going to have a local minimum. And then for part B there, if again we have that f prime of c is equal to 0, and then we are concave down, you're going to have a local max there. If f prime of c is equal to 0 and the second derivative is also 0, that means the test is inconclusive. It means it's a bad question, and you just kind of move on from there. So let's go ahead and get down here to our second example. Let f of x equal that nasty looking thing, and we're going to find all critical points of f. And then we're going to find all c values where f prime of c is equal to 0. We're going to use the second derivative test on all the c values to determine the local extrema. This one can be a bit of a bear, so this is really good practice for you to go through this derivative and look at everything. This can be a little nasty. There needs to be some good factoring in there as well. It's really going to test our algebra skills and really test our ability to use the correct amount on the paper, because I know that there's a lot going on here. So I'm going to quickly use the left-hand side for a lot of this front-end work. So we need to find the derivative. There's going to be some product rule here. So we're going to take the derivative of the first here, which is going to give me 1/3 x to the negative 2/3 times this 3 minus x stays the same, plus x to the 1/3, and then we're going to do the derivative of the squiggly line right there. That's going to give me a 2/3 3 minus x to the negative 1/3. And actually, when I do that, there's a bit of a chain rule there. Times the derivative of the inside, which is negative 1. I'm going to rewrite this a little bit before I take out a GCF. So I'm going to rewrite this as 1/3 x to the negative 2/3, 3 minus x to the 2/3 minus 2/3. That minus came from that negative 1 that we had earlier. 1/3 and then 3 minus x to the negative 1/3. Okay, so I will need to take the second derivative of this very shortly, so I do want to clean this up a lot so that that second derivative isn't as nasty as it really is going to be. It's going to be nasty one way or another, but let's just clean it up a little bit. And not only that, I also need to set this equal to 0, so I'm going to clean this up a lot more. Let's find some GCFs. That makes our life much easier. I see a GCF of a 1/3 is going to help us out with the constants. We're going to take out the x to the negative 2/3. It's going to make the x terms much nicer, and the 3 minus x to the negative 1/3. So I'm going to pull out a 1/3 and x to the negative 2/3. The reason I pull that out is because I'm going to pull out the smallest exponent, and then 3 minus x to the negative 1/3. And that's going to leave us with the first term is just going to be 3 minus x. I'm going to put that in parentheses just so I know it's wrapped up nicely. And then minus, I know there's a 2 there. The 3 minus x term is gone, and this is going to leave just an x. Yeah, that's it. I will set this equal to 0 very shortly. I can rewrite this all very nicely, actually, as put that 3 in the bottom. Put that x to the 2/3 on the bottom, so to make it positive now. I'm just going to be writing all this stuff to be in the bottom, and then on the top there, I get 3 minus 3x, which that 3 can factor out and cancel out with the 3 in the bottom. What are we doing here, folks? We got an easier one on us. I thought this was going to be a little bit tougher. Well, it will be. And I want to find critical points that set that equal to 0, and actually, I'm going to have x equal 1 here. If I'm going to set that equal to 0, I'm going to get x to equal 0, and I'm going to get x equals 3 as my 3 critical points. I do have 3 critical points here by taking each factor setting equal to 0 in the numerator and the denominator, but for the second derivative test, I only care about c values where f prime is equal to 0, so I'm going to reject those bottom ones and actually just say that I just have c equals 1 is the only one I care about. I do have critical points at 1, 0, and 3, but I'm going to reject 0 and 3 because those are not useful in the second derivative test. Okay? So now we're going to go ahead and find the second derivative, and we're going to substitute in a 1 into that and see if we're positive or negative. Hopefully we're not 0, because that'd be a waste of everybody's time here. The second derivative here, I do note right here that this is my f prime. So I have it on the screen for us. It's gonna be a little tight here. So it's gonna be low d high minus high d low, since we do have quotient rule here. So low here is gonna be x to the 2/3. 3 minus x to the 1/3. The derivative of the high is just -1. Minus high. D low. I'm going to put this a big old bracket there because we got a lot going on. And we're going to do product rule. So derivative of the first here is going to be 2/3 x to the -1/3. Looks kind of familiar to me. It's almost like what we just did in it's like the reverse of the derivative, actually. The 1/3 and 2/3 flipped places. And then, I don't even know if I can even, well, am I going to be able to fit this? Plus, I'm going to have to squeeze this on in here. That stays, that's x to the 2/3. And this is going to be, don't forget about that -1 that comes out as well. This is going to become 1/3. Actually, I'll make this look a little bit nicer. There's going to be 1/3, so times 1/3, 3 minus x times -1. It's there. Bracket done. And then that would be to the -2/3. I know I'm squeezing it in there. You'll survive. All over the bottom squared, which is going to be x to the 2/3. 3 minus x to the 1/3. Okay, so now, let me see if I can, there, you can see the whole second derivative right there. All I care about, I'm not going to simplify this. This is nasty. I do care about substituting in that 1, though. That's all I care about here. So f double prime of 1, and what's nice is it's 1. It's going to clean everything up a little bit here. For that first term, I'm going to get a 1. I have a -1, so I have -1 times, that's going to be 2 to the 1/3, so -2 to the 1/3, minus, here's the nicer part about it, I'm going to substitute a 1 into the second part, and since I'm substituting a 1 in that second part, I zero everything out, because that first term becomes 0 times gobbledygook. Who really cares? So that's going to be that all over. If I substitute a 1 down here, I'm going to get 1 times 2 to the 1/3. So that's all nasty. That gives me an answer of -1. Just a little bit of arithmetic and algebra goes a long way here. So since that's -1, do we have a local min or max? You can look right up here for our second derivative test. Since our second derivative is negative, that's going to be part B right there. We have a local max. So we have, so f has a local max at x equals 1. Because f prime of 1 is equal to 0. This is required, so you have to state the hypotheses here of and the conclusion of the second derivative test. So because f prime of 1 is equal to 0, and f double prime of 1, I already said it's -1, but I can just say that it's going to be negative. So this is me using the second derivative test because the directions specifically told me you must use the second derivative test. Now, you could find out this by doing the first derivative test, and they can find the extrema, but they're going to find out when we're increasing, decreasing, and that's probably not too bad on the first derivative there, but we had to go through and do the second derivative test, so that's why we did all of that lovely work right there. Okay, let's look at this next problem. Suppose that we have the function f is continuous, it has continuous second derivative for all x, and that we have f of 2, value of f of 2, value of f prime of 2, value of f double prime of 2, and let g be a function whose derivative is given by, so we have g prime here. We don't know much. Does g have a local minimum, maximum, or neither at x equals 2? So, if we're trying to look for local maxes or mins, we have to use the first derivative test or the second derivative test. Now, we cannot use the first derivative test here because the first derivative test tells us that we need to go from increasing to decreasing or vice versa. We don't have enough information about g prime because we're limited on the value of the f function. We know very little about f. Because of that, and f is inside of g, we do not know much about g, so we are handcuffed here. We must use a second derivative. Well, first off, if g prime of 2 gives us a value that is not 0, then this is going to be irrelevant for us. So let's go ahead and substitute this in. So g prime of 2 is equal to 2 squared plus 4 times f of 2. times f prime of 2. And let's substitute the values I have in now. Because if this is not 0, we don't have any extrema here. Because in order for there to be extrema, we'd have to have a critical point, which means that the derivative at 2 has to be 0. Why did I write 2? Nobody knows. So we're going to get 4. F of 2 is negative 1, so it's 4 minus 4 times f prime of 2 is 4, which gives me 0 times 4, which is 0. So g prime of 2 is 0. We are eligible here to use the second derivative test, and let's hope that we get a positive or negative value. Because if we get 0, we got a bad question. So let's real quickly find out what g double prime of x is. Again, we have some more product rule here. So the derivative of the squiggly, which is first, is going to be 2x plus 4f prime of x. And that was the derivative of that squiggly term. Plus, we're going to leave that squiggly term now. Times the derivative of the straight underline one, f double prime of x. I don't need to simplify it. I just need to substitute in a 2 and see what I get here. So we're going to get 4 plus 4 times f prime of 2 times f prime of 2 again, plus 4 plus 4 f of 2. Some of you might know where we're going in this one. I don't know why I put so many parentheses there. I got some problems. F double prime of 2. So if I start to simplify this a little bit, I'm going to tell you this right now. I know this is equal to 0 because I just did that way up here. I know that's equal to 0. So cool on that one. So I'm going to get 4 plus 4 times 4. Just by doing substitution here, and then times 4 again. Oh gosh, is that 80? I'm asking you as if you're going to respond back to me. It better be 80, because if not, I just made some bad arithmetic errors. So we know that this is going to be a local min. So G has a local min at x equals 2 because, first off, G prime of 2 is equal to 0, and G double prime of 2 is positive. Just to remind you back up here, whenever we are positive with our derivative, we're going to have a local minimum. So we have a local minimum here. We justified it. This is exactly what we need to see. Do not forget to like and subscribe if you like videos like this. You want to see more stuff like this, I'm happy to help you out. Just don't forget to like and subscribe.